So for the folks who are not here on Friday, this is approximately what our timeline is going to be here. We did some vocabulary on, oh, sorry Alex, did I have to tell you? Go?
No.
On Friday we did some vocabulary. I'm just going to put up the words here so you all know what we covered. Then today we're going to actually start our medical image segmentation project. We'll finish it up on Tuesday. Wednesday morning is the exam, and that's when the second and the last problem set will be due also. Okay. Oh yeah, just to note, the recitation is going to be right after the lecture ending. There's going to be no, 1 o'clock or 2 o'clock section. Okay. Okay. All right. So here was the vocabulary from Friday, what we reviewed. The only new item here was the Gaussian PDF, and the reason I want to repeat that once more is because that is the only part of the Friday lecture that we're going to carry forward with us for our MRI segmentation problem. All right. The picture is for the Gaussian. The x-axis is still labeled y. And I'm going to ask for a volunteer to try filling in the question marks for this Gaussian distribution. On the right is the expression. Anyone want to take a stab?
The bottom three question marks are variance.
Okay.
The variance outside the...
Outside? Uh-huh. Is it variant? Is it sigma squared or sigma outside? So standard deviation.
Yeah. Okay.
Right? Okay.
And is that the same as the variant? I mean, would that be the variance inside under the square root? And
yes. Yes. Yeah. So that's the thing to remember. If it's going to be inside the square root, then you have the variance itself. But if it's outside, it's just the standard deviation. Okay.
And the one question.
One question mark is the mean. Well, it's x minus the mean.
It's x minus.
Right. Okay. Yeah.
And the 2 question marks is the variance.
2 question marks is the variance, right? That has a square. So 2 reasons I want you to be able to do this without even a template. One is just, it's very empowering to be able to write down a Gaussian. Okay? You have to, 2 years from now, you're going to just be able to whip out a Gaussian. And the first grad class I took where they went over Gaussians was the professor. I'm going to do something too that the professor did to us, and he told us the first day of class that he was going to have the expression for a Gaussian on our final exam. That was going to be the first question, and half of us still got it wrong. Okay? But I'm going to tell you, we're going to have this, maybe not as the first question, we're going to have this on the exam simply because I want you to be empowered. I want you to be able to whip out a Gaussian. So when you have to write it, you have to remember where the squares, the square roots, and just someday down the road, you're going to feel cool for knowing it. But right now, you got to suffer through it. All right. So here's the expression. And does everybody have a sort of an intuition for how to, if we didn't have the picture for the Gaussian up there, just be able to look at the expression approximately and be able to tell the shape of the curve? Someone want to take a stab at that? We went over this briefly on Friday. The fact that it's a negative exponential. What does the graph of a negative exponential look like? It's going down, right? And that's basically, and because you have a square in there, you're on both sides of the x-axis, of the y-axis, right? So there's some things you can tell about the shape of a graph. You can just intuit that without really having to plug in values, right? All right. So on Friday I said in sort of vague terms that we're going to do a real-world problem, and we talked a little bit about MRI images. So I'm going to refine that goal today, that the real-world problem we're dealing with is segmentation of magnetic resonance imagery. And I'm going to remind you with this picture again of what that is. On the left here is a magnetic resonance scan of a patient's head. And as you see, I'm just scrolling through these slices. Can you guys, is the contrast sort of okay? All right.
Not easy to see.
Not easy, yeah. I know, it's, I tried to turn off the lights, but it wasn't doing a whole lot better, so I have an image later on, which maybe it's, approximately here's what this, so this is the profile This is the nose here. That's the back of the head. And these are slices taken along what's called a sagittal plane. So these slices, the way they're reconstructed is the slice you're seeing up front really is the middle slice like that. And then everything subsequent is just, we're moving out towards the side of the head, towards the ears. Okay? Oops, what happened here? Oh. All right. So that's what an MR scan looks like. It's a stack of two-dimensional slices. And the scan that we're going to deal with in the lab is each of the images is going to be 256 by 256 pixels. And there's 124 slices in the scan, but actually I've only put one slice on the Ars Digita site because I wasn't quite sure how to make folders in the homework directory. I didn't want to put 20 images there, but is there any way? Does anyone know how I can make folders in the assignments? Oh, that's right. Yeah.
You could upload them to
some other.
the file server.
I may, yeah, I have the files on a disk, and I just didn't, where you see the homework right now, there's, in addition to the homework, there's a couple images, and I just didn't want to put 20 images right there. And, okay, so, yeah, we'll have to.
If you have your own site, you can put there, just bypass.
I'm sorry?
If you have your own site, just put them up there.
Actually, yeah, they are there. Yeah, I do have them. I do have them on my website. So, well, yeah, that's something that I'm sure it'll come up is because you start doing the problem set. There's only one image. I put one MR image in there so you can get started, and then we'll do the rest. Okay, so back to the segmentation problem. You start with an MR image like a stack of MR two-dimensional slices, and end up with a labeling of the slices so that at each pixel, instead of just an intensity value from 0 to 255, you end up with a label which says this is gray matter or white matter or fluid or whatever else. Once you have that labeling, then you can render that into using the image on the right. That's a surface rendered image. We're not going to do the surface rendering part. Maybe in the end, if everybody finishes all their problem sets, we can get into that. But what we'll do is an intermediate stage. We'll create a label map or a segmentation from the 2D slices, which can be piped into a surface renderer later. Okay?
Do you do it in 3D with stereoscopic glasses?
People do it, yeah. People do it. In fact, that's it was a fad a few years ago, and it's coming back now. I had a customer come up to me and say that, can we do that? They wanted it for presentations, not in surgery. In surgery, it's just hard because the baseline keeps varying. You can't. You don't, with the stereo displays that we have right now, you can get a very nice, just for cosmetic reasons, very nice, but it's not a very accurate rendering. So in surgery, the surgeons don't want the stereoscopic display, but for presentation purposes, surgeons who are doing research stuff, we want it. Yep. Okay, so here's what I'm planning for, what I've planned for today and tomorrow. Well, in the lectures, I'll go over how one does Bayesian segmentation of MRI. You guys have seen Bayes' rule. You'll see MR images, and there's just putting the two together. How does one actually implement a Bayesian segmenter for MR? And then in the lab, we're just going to very tightly follow what's in the lecture. In fact, what I did for the next two lectures is I did the lab first to make sure that in lecture, all I'm doing is covering how we're going to implement that lab. Okay. So here's how the inputs and outputs of a Bayesian segmenter work. Let me see. Okay. Here's an example input image that will go into our segmentation algorithm. Okay. Now, if you remember, if you could see the images in the previous, the MR slices, you would have noticed it's a sagittal. Those were in a sagittal plane. They were cut like that. This is an axial. Axial, actually, this may be a. Never mind, I take that back. This is actually a coronal cut, which is like that. No? Was that disagreement? Sorry. It is coronal, thank you. So this is a coronal cut. Typically, when you have an MR scan taken, the surgeon will decide, or the radiologist will decide that for the particular pathology that the patient has, is it better to get the scan sagittally? Do you want to get the slices like that? Do you want to get them axially, which is along the long axis of the body, or coronally, which is the third one? Okay. So this one is a coronal cross-section, and you can ignore the labels that are here. The ones that I want you to notice, and we're going to use this in the lab, there are three structures I want you to pay attention to. One is gray matter, which is the gray outline of the brain tissue. Just globally, this is the brain tissue here. This out here is the skin surface. Okay? So this gray matter is the gray outline of the brain. The white inside it, that's the white matter. Okay? And the black here, this is cerebrospinal fluid. Okay? So there are three structures that we're going to be interested in segmenting out in the lab. White matter, gray matter, and CSF. Okay? Now, these are some additional labels. This was a picture I pulled off the web, so they were doing other things with it than I needed. But that's the important thing. White matter, gray matter, CSF, and you've got to remember these because right now in the lab, this is the only place that I'm mentioning what is white matter, what is gray matter, and what's CSF. So when the lab refers to them, you can pull up this lecture, and there's no label in there, but you can come ask me.
Repeat the distinction between white and gray matter. I don't really.
Oh, you don't see? Okay.
On the
Okay. Let me come look from where you are. So in the brain tissue, brain is the big mass in the middle of the bone, right?
Sure.
Now, if you look at the periphery of the skin of the brain, that's gray matter. Okay, it's darker. There, you see a dark outline. In the middle is bright, very bright area. That's the brain. I mean, that's the white matter. Okay. And then there's a cortical. If you think it's just a layer.
Kind of like a ring.
Yes.
Kind of.
Now that ring, the part that's the ring is actually fluid.
Okay.
Okay. So in the brain, there's the internal part of the brain tissue is white matter.
Okay.
And there's a boundary. There's a thick outer cortical gray matter, which is. So if you think of it, there's the axons, the nuclei and the fibers. Okay. So the nuclei sit in the gray matter.
Okay.
The fibers are actually going in the white matter.
Okay.
Okay. So this convoluted boundary of the brain, there's a grayish, and it'll be when you look at the images that we have, it'll be quite clear in them.
Okay. Okay.
So, but come get me because that's important. When you pull up an image, come get me and I'll point it out to you. And by the time we're done with the segmentation, you'll be able to see it much more clearly. And partly that's the goal of segmentation, to not have this haziness. After we're done segmenting, the white matter will be, blue, and the gray matter will be purple or whatever color you choose. So then I won't have to go through shades of gray with you. All right? Okay, so this is going to be the input of our system. Any other questions at this point? The brain shape, the brain has all these folds. The sulcus, the sulci, and the gyri, the folds of the brain. And just the outer layer is darker, and it's gray matter. And the inside is brighter, and this is all white matter.
I can see why we need a segmentation model.
Yeah. Yeah. Still have doubts about axial, coronal?
I think it's axial.
You are? Okay.
It's horizontal.
Yeah.
Those must be the nasal cavities.
This must... Well, see, I was thinking it was coronal because I was thinking maybe these are the eyes. But I could, that's what happens when you pull things off the web.
It's gotta be.
It's got to be.
It's on the two sides.
Yeah.
I'd have a neck or a...
Well, even in coronal...
The shape of the ventricles looks like it's axial.
Yeah? Okay, we'll go with axial.
I'm used to seeing all the slices together. So
Yeah. No, I'm not sure about this actually because mostly I work with sagittal. So between axial, so if we saw axial, we would probably see, at this level of the ventricles, we would probably see the eyeballs, would you say? No? All right, well, I'll look, yeah. It's not as important to the lab. But we will get this. All right. So now we know what the input to our Bayesian segmenter is going to be. Now, the knowledge base that goes into solving this problem is the following. There are two things. First one I already mentioned to you. We know that we're going to be segmenting out three classes, white, gray, and CSF. Right? another very important piece that goes into using any Bayesian method is you have to have a training data set, which in our case is going to mean we're going to have some images that have already been segmented into these classes by an expert. Okay? So we will have a set of images, MRI images, in which white matter, CSF, and gray matter will already be labeled by an expert neuroanatomist. Okay? So in fact, what you'll be able to do in the lab is pull up an image and its segmentation right next to each other, and then you'll know exactly what's white, exactly what's gray. Okay? All right, and the output of our segmenter is going to be a segmented image or a labeled image, which will have, instead of the original 0 to 255s, we're going to have 1, 2, and 3 as the labels. Where 1 is going to be white matter, 2 is going to be gray matter, 3 is going to be CSF. And then we can color code them however we want. Okay. All right, so in order to be able to actually go through the mechanics, I'm going to revisit Bayes' rule one more time. Okay? This is the standard form that you've seen it in earlier in this class, right? What I'm going to do is next I'm going to make specific definitions of the events A and B so that we can use this for segmentation. Okay. And we are going to use these, oh, sorry about the font.
No, not at all.
I was trying to make this bold and larger, but couldn't happen. So this is how, these are the equations you need to pay attention to because we're going to be coding these up in our problem set. Okay? And here's how it goes. Up here, so let's try to make parallels between the A and B up there and the events that the actual instantiations of the events that I've got in here. The slides are on the web too if you want. Okay? So I'm just going to describe to you what A is in this equation here. So A, clearly you can just see by displacing it, it's gamma I. The definition of event A in our segmentation problem is going to be that the event that tissue class I, okay? The pixel we're looking at is tissue class I. And by gamma I, I'm going to use this over here, just this terminology is going to be important as we start implementing it. What I've done is used gamma i's to encode tissue classes. That's the random it's a random variable, and it's a discrete random variable, which represents tissue classes. All right, you got the sprintf? Yeah. And what we're going to do is here, when I is 0, that's white matter. When I is 1, that's gray matter. That's going to refer, so gamma 1, when I say gamma 1, that's going to be white matter will be the tissue class. Okay? Actually, let's call them 1, 2, 3, just because MATLAB is offset from 1. 3 is CSF. Okay? So the event in our equation up there, the gamma I, probability of gamma I given x in terms of A and B, it's the probability that tissue class, when we're looking at a voxel, or, okay, a pixel, there's some terminology here I want to get clear. Pixel is one entry of our image. Okay? Voxel, sometimes I will call it voxel because when our data set is actually not just two-dimensional, it's three-dimensional. So a pixel in 3D is referred to as voxel. Okay, so it's just a location x, y, z in the image, where the z comes from which slice you're at. Okay? So gamma I is the event that the voxel that we're looking at belongs to tissue class I. Okay? And P gamma I given x is the posterior probability that if the tissue intensity is x, the class is gamma I. Making sense? That's the posterior probability. Just as probability of A given B is the posterior probability that event A has occurred, given that you know that B has occurred. That's what probability A given B refers to. Right? So going into our segmentation world, its probability gamma I given X is exactly the probability we want to find. It says, what is the probability that I'm white matter given that my intensity is 20? Okay? That's what we're trying to compute. The left-hand side of Bayes' rule is exactly what we want to compute. Okay? Now let's look at how we're computing it. We'll look at the right-hand side. The first term is probability of X given gamma I. Anyone want to take a stab at what that is? Probability of X given gamma I in our segmentation context.
Probability that, say, white matter would show up with intensity 20? If you had white matter?
Yes. I don't know if you guys are familiar with the term class conditional density. I think we've thrown lots of terms at you, but probability of X gamma I that's what's called a class conditional density. It is the probability. So for example, if I gave you, I took some training data, and from that I looked at all the pixels that were white matter, okay, and then plotted all their intensities. So the Gaussian function that we've written, for example, if I computed the Gaussian using all intensities of what was white matter and plotted them, if I told you that this is what, I'm just going to call it, that this is what the probability density function for white matter looks like, if this is what I told you, this is the class conditional density, okay? This is the term that probability of X given gamma I, that if I tell you, okay, you've got an intensity 90, what is the probability that this belongs to white matter? So what you do is you look at your representation, the model that you have for white matter, and you plug in the number 90 here, look up on your Gaussian, and you come up with this. Okay, you say this is probability that a given intensity value X belongs to white matter.
So is the 100 common across all people?
I'm going to wave my hands. No, it's not. It's not, and that's what makes segmentation a challenging problem. That what we're going to deal with in this class is we're going to take one data set. We're going to make some of it a training, from one patient scan. We're going to make some of it a training data set, meaning that out of 10 slices, what I'm going to ask you to do is take 9 of them, use the manual segmentation, meaning that somebody's already told you which pixels are white matter. Now you're going to go, that index 1 through 10 in the image, say, is white matter. You're going to look at the intensities for those pixels, and you're going to come up with the Gaussian. And then you're going to use that to segment out the remaining one slice from that data set. How good is that model going to be when you go across scans? Not very good. We're not going to get into that here, but there are lots of techniques. People have spent years just figuring out how to normalize scans across patients. And there are some, intuitively, why is that a difficult problem? Why is it that if I give you from one scan, if I come up with 100 as the mean for white matter, what's your guess for why that's not a good estimate for the mean for the next patient? Anyone want to venture? Why is it that an MRI scan will not have the same intensities or intensity ranges across patients for the same structure? What?
I'm curious, among one patient, does it vary from scan to scan?
That variation is much smaller, but there is some, and that's one of the reasons for that. One of the major reasons for that is that when you go, if you ever see an MRI scanner, and if we get a chance on Thursday or Friday, I'm going to try to do a field trip for us to Brigham and Women's so we can, go see an MR scanner there. And there's, the console is huge. There's like 2,000 buttons. There are people who train for, I think, a full year on how to use the different buttons on the scanner. Okay, so the combination, so for every surgeon tends to have their own protocol for how they want the buttons pressed on the scanner to get you their image that's optimized for the procedure that they're doing, the diagnosis they're used to, and sometimes just that's their protocol. At Brigham and Women's Hospital for neurosurgery, there's a protocol called Protocol 55. We use it. Who came up with it? I don't know, but it defines things as how much time to apply a pulse to the MR. Let me tell you a little bit. I'll give you a 2-second version of how MR works. anyone here familiar with how MR, the process of magnetic resonance imaging works? MR, you want to take, I have my 2-second explanation for it, but if anyone wants to go into a little bit more. No volunteers? Okay, I'll give you mine. You're smiling back there. No? You can tell me, but here, this is the way I was first explained how MR works many years ago, and in spite of having taken classes on it later, this is the explanation that always sticks with me, and I'm going to try that on you guys. It's basically what MR is, what we're measuring in magnetic resonance imagery is the precession of protons, okay? So here's how you think. If in the brain, in tissue, there's water, okay? And water has protons, hydrogen atoms. Okay, they're charged particles. All right. Now, if you take charged particles and put them in a magnet, they're going to line up with the magnetic field of the magnet. So think of your head not as having a brain in it, but just think of it as little precessing protons here. Just think of these. This is what these are the things you've got in your brain. All right. So this is your brain outside of a magnet. All right. And then we put you in a magnet. Let's say this is the bore of the magnet, and this is the magnetic field. This is what? This is what's happening to all the protons in your brain. Okay? Now, different tissue types in the brain have different amounts of water in them. Okay? Now, so they're going to have different amount of protons in them, if you will. Right? Now, but they're all lined up. When you go into a magnet, when you go in for an MRI scanner, aside from being claustrophobic, no, you can be freaked out that your protons are lining up. But you're going to go there, and you're going to, all these protons are going to line up, and there's no difference between how they line up at that point. But the magic of MRI imaging is that there's a second pulse that comes in and excites these protons. So if you ever go in a scanner, you'll go in after a few seconds, few minutes, you hear this loud banging noise. What they're doing is they're applying an RF pulse. And what that's doing is, it's making all your protons do a 90-degree flip. All right? Then what happens is they take away the pulse, and these flipped protons now want to go back to their natural state, which is under this main ambient magnetic field. Okay? Now, the fact that now in the absence of the second pulse, there's different amounts of times that these protons take to come back, depending on their density in the tissue. For example, fluid, like cerebrospinal fluid, it's got a lot of protons, okay? Gray matter or hardened tumor or bone doesn't have a lot of water and hence doesn't have a lot of protons, okay? So the time it takes these protons to come back actually depends on the amount of water content in that material, okay? So, they all lined up good, they all flipped 90-degree good, but when they're coming back, now they're starting to show their differences. So that's what's called a relaxation time. The time it takes for these flipped protons to come back to their natural states when the RF pulse is removed. And that is what is different for different tissue types. And when we measure that, that's how we can differentiate between. So the image that you're seeing where gray matter is a different intensity than white matter than fluid, that's actually proportional to the time it takes for these protons to come back after that RF pulse is removed. Okay? Make sense? This is the only part of the MR imaging that I've been able to intuit. The rest of it is, okay, you apply a gradient field, and then you start, the shortest answer I can give for that is you apply a gradient field and you know the different gradients that you're applying at different locations. And that's how you know where the data is coming from. That's the, I'm not one with that explanation like I am with the precession. I would, if you had asked me a couple months ago, I would have said yes, except I was talking with a surgeon the other day from NYU, and he's been doing these experiments where he's seeing a lot of, he's imaging a bunch of phantoms, and he's seeing a lot of distortion in these GE scanners. So the short, pedagogical, the answer is yes, they're very accurate, but people are finding out that there are some cases in which you don't get very accurate imaging. One of the known conditions where you don't get very accurate imaging is that if you're imaging in a plane that's tangential to the structure you want. For example, if you want to image cartilage, okay? So the cartilage sits like, the femur, and the femoral cartilage is sitting right underneath it in this curved shape. And if you're taking slices like that, structures that are tangential to the imaging plane don't tend to show up well. And I think there's some that's probably due to the way discretization is done. There's, these images, there's Fourier domain, then you transform them into the spatial domain, and I suspect that there's a very clear-cut explanation for why that happens. I just know the effect. So there are optimal directions in which to scan so that you maximize the signal and minimize the artifact due to the MR process. But for the most part, people do consider MR imaging to be the best modality out there for soft tissue contrast, which is tumors. That's okay. Okay, so now we're talking about the millions of buttons on the MR console. So that's what these buttons control are. What is the pulse you're going to apply? For example, what is the RF pulse that you're applying that's going to make the protons flip? How long are you going to apply it for? What is the how strong do you want that pulse to be? When do you want to start measuring the relaxation time? Do you want a long relaxation time, short relaxation time? All of these things lead to very different looking images. There's T1 weighted images, T2 weighted images, gradient echo images. So if you just say, I want 2 MR scans of the same patient, one of the things you've got to say is use the same protocol. Okay? If you're using the same protocol, images look, it's fairly easy to model the differences between them. So it's not a big deal. If you're using exactly the same protocol with the same settings, you're not modeling based on intensities from one is going to be just as good. Another aspect is, did you inject the patient with dye or not? Gadolinium is a typical contrast enhancing agent that's used it'll make the tumor shine. You inject it into the patient, gets sucked up by the blood, and in the tumor, there's usually, there's a lot of blood flow to tumor. So it's wherever there's a lot of blood, that's where gadolinium goes fastest. And that's what it's going to make in the MR image. It's going to have, the tumor is going to glow, and everything else the contrast will be suppressed somehow. So every surgeon has, and radiologist has their own protocols for what they think the right set of parameters for MR are, so they can get the best images for their patients. Okay? Now, there's, in addition to, the MR imaging protocol variations, there's other variations such as there are different, if you image a patient without a pathology and with a pathology, for someone without a tumor and with a tumor, or with different types of tumors, there's structures that are missing in one scan that are present in another. Okay? Now, if you think about it, this MR image that we've created has a fixed set of intensity. It's a fixed intensity range that it's allowed. MR images typically that are put out from a scanner have 12 bits per pixel. We're dealing with 8 bits per pixel in our lab, but there's 12 bits per pixel allowed, meaning that every intensity value that's captured for a particular location has to be rescaled from 0 to 2 to the 12. All right? So if you think about it, we won't go to 2 to the 12, but let's say if you have if you're allowed a dynamic range of 100, okay? So you're told that no matter what's in this patient's head, I want you to encode it as a number between 0 and 99. You have 100 values, all right? So now if that patient has a lot of tumor that's very bright, okay? Let's say white matter is the brightest structure in one patient's brain, and tumor is the brightest structure in another patient's brain. The way that the MR process is going to encode this into images will be that tumor will be 100 in the patient with the pathology, but white matter will be 100 because the scanner is set up so it uses the full dynamic range available to it. Okay? So the fact that there are different structures, some people have bigger sinuses than others, right? So it's like the dynamic range gets, all of these influence the dynamic ranges of MR imagery. So being able to say that 100, white matter is going to be a Gaussian of standard deviation 3 centered around 100 is, you can only do that in a class. So we're not, but the nice thing is people have been working on this for about 8 to 10 years now and have come up with ways for coping with these differences, not just across scanning protocols, but also across patients. If you guys ever stick with this field, you'll learn all about it. It's my little promo. Okay. All right, so what I'm debating here, this lecture material really covers what we're going to do today and tomorrow. So what I'm going to do in the next 5 or 10 minutes is go through, starting from here, the next couple of slides, I'll go through them not very fast, but not very slow either. But we're going to go through it again. I just want to have you see all this material, know that it's on the website, and use as much of it as you need in the lab, but we will go over it again tomorrow. So don't worry if you're sort of lost. But if you're completely lost, come get me. All right. So here's recapping this. We sort of got halfway through this equation. But here, what we're doing is we're trying to determine in a Bayesian setting what is the probability that I am white matter if my intensity is 90. Okay, that's the expression on the left. And the way we're doing it is we have, remember from our training data, we're going to have a Gaussian for white matter. We're going to look up 90 in that Gaussian, see what that probability is. That's going to be the probability of x given gamma I. Okay? Then the next term in there is probability of gamma I. That's the prior probability that a given tissue, a given pixel is white matter. Okay? Now, where does that prior come from? Well, for the purposes of this class, we're just going to make that a uniform prior. We're going to give it no information. But there are cases, and we'll talk about them tomorrow, where you could have more interesting priors. The term at the bottom is a normalizer. That's the marginal probability. We've seen it before, and I'll reiterate that maybe in the lab, maybe tomorrow. Okay, so I put this little note here just so you guys are familiar with the terminology that I've used in the lab handout. Probability of x given gamma, or there are no subscripts there, that's the class conditional probability. That's what I'm calling the class conditional probability in the lab. That is going to be the Gaussian that we construct from the training data. So if somebody already tells you, here are the million voxels that are white matter in this data set, you can go off and construct a Gaussian from that. That's going to be your class conditional density for white matter. Okay? Probability of gamma, that's the prior probability. That means if I didn't show you any data at all, I didn't tell you what the intensity is, and I just said, okay, I'm holding an MRI pixel in my hand, what do you think it is? If you knew nothing about it, what would you say? You'd probably be well off here saying that it's white matter. Simply because if you remember from our scan, most of the junk in the middle, that was white matter. Most of the stuff was white matter. There was gray matter just around the surface and a little bit of fluid. Right? So just your odds of getting it right are if you pick the class that has the highest number of pixels on it. That's the sort of information one encodes in a prior. Okay, that's probability of gamma. Then the third one is probability of gamma given x. That is the posterior probability. That's saying that, okay, now you know what your class conditionals are, you know what your priors are. Tell me finally that here's a pixel value, 90. What do you think is the probability it's white matter? What does gray matter? What's CSF? Because, damn it, I want to make a decision on it. Right? That's the final thing. Probability gamma given x. That is what we're going to be computing in our problem set for all of our classes. Okay. So here are the mechanics, and we'll go over these again tomorrow, but I'll just say them here once, that the way we're going to do the segmentation is, first thing we're going to do is take the training data we've got, and from that create class conditional density models. Okay? That's what these Gaussians are. So what we're going to do is we're going to take a slice, or all slices that we have, in which white, gray, and CSF have been segmented. We're going to take all the pixels that have been labeled white matter, take their intensities, make a vector out of those, and compute a Gaussian from that. That will be the class conditional density model for white matter. Anyone follow that? Sort of? Okay, it's okay to, especially if you haven't gotten to the Gaussian, the first part, it's okay to just tuck this information away someplace and then come back to it, because that's what we're going to be doing. That's going to be the part of the lab that you will not be able to get to unless you understand what's going on here. And I'm going to repeat it tomorrow, and I'll go around and repeat this as we're in the recitation also.
So we're just going to use some statistical formula for median standard
Yeah, that's the built-in MATLAB. Yeah, that's right. Yeah. Okay, so for our lab, we're gonna use uniform priors on the classes. Okay, so if we've got 3 classes, we'll just say that the P of gamma I is always going to be 1/3. All right, and then we're going to use Bayes' rule. That's from the 2 slides ago, the formulation of the Bayes' rule that I had in there. We'll use that to compute the posterior probabilities. Okay?
Given x, gamma I given x.
Say that again?
A posterior is the probability of gamma I given x.
Exactly.
Intensity.
Exactly. Yes, that's what we're going to do. That's exactly what we're going to do. And then we're going to assign the label. You know, the way we're going to create the segmented images, we'll look at all the posterior probabilities, and then we'll assign the label, and I say map here, maximum a posterior probability. That will be the segmentation. So at this point, you're going to have the 3 posterior probabilities, right? Probability of gamma 1 given x, gamma 2 given x, gamma 3 given x. And there are MATLAB constructs that, you know, I'll go over in the recitation. Is what you, for each pixel, you'll just go and look at which one is the highest probability. And then you'll say, if this one was the largest, you say you're going to assign a label 2. And that's how you're going to create an image which will only have labels 1, 2, and 3. And we can display that in MATLAB, and that'll be your segmentation. Okay? Okay, that was it. And what we're going to do, there are a couple pointers. You know, I've tried again to make the problem set so that it walks you through the constructs you need. But one of the things I want you to just keep in mind is when we read an image, it's a 2-dimensional array. Okay? In order to be able to reuse the routines you wrote for Gaussians before, and in general to use MATLAB most effectively, the first thing you're going to do with the image is just linearize it, flatten it out into a 1-dimensional array. Okay? And if you have, let's say, if image is a 2-dimensional, okay, if image is a 2-dimensional array, then the way you get a 1D image from that is the following, or let's call it image 1, open paren colon. Okay? So this is just going to flatten out the image so it'll be a 1-dimensional array of all the intensity values. Remember, we're not doing anything with the spatial location here. The fact that intensity 100 occurs up here in the image or down here doesn't make any difference to its segmentation. Okay? So flattening out the image and just using the intensity values will make your life a heck of a lot easier, and you'll be able to use a lot of the vector operations of MATLAB without having to write, you know, nested loops that go through each pixel. So if you ever find yourself writing any nested loops in MATLAB to do any of the image processing I'm talking about here, find me. Send me an email if I'm not here, call me. Okay? Because we don't want to be doing it that way. It'll be very slow, and it'll be some cool MATLAB construct you've missed. Okay? And I'm hoping you'll discover them as you go, but I know that it took me many years to learn these effective ways of using MATLAB, and I'm expecting you to pick them up in one day. So, so come find me. If you ever find yourself writing a loop here, which is going through, for, x equals 1 to 256, y equals 1 to 256, doing something for every pixel in the image, there's a faster way to do it. Okay? All right. Any questions here before we break?